All right, start recording. You're good. All right. Well, I'm gonna start the lecture, and I will show you guys don't have to ask each other because we have the graphs. So exam one results, no individual scores. Okay, we only show the adjusted score distribution. So we have two. So this is the person who was. This is the like 100 percentile. This is the highest score. Second highest score, I'm using the third highest score as the new 100%. So that's why it is adjusted. Everything is kind of scaled accordingly. So the break point for A's is about here. It is a 3.5. So basically this many people, okay, just count the number of ticks, are getting A's. B's are from 2.5, which is about here, to 3.5, which is about here. So these people get B's. I don't get a whole lot of people getting C's this time, maybe just one or two, and then some D's and F's. So, so that's one way to look at it. This way, you can actually look at your own score and you kind of know where you are placed in class, which is not important in this class, I don't think. In other words, if the lowest score is here, that means the whole class is doing really well, and I don't have a problem with that. So, and then the actual distribution is like this, which is I think that is pretty good. Okay, seven people after adjustment got A's, six people got B's, one person got a C, and then two people got D's, and one person got an F. That's it. All right. So, any questions about the distribution of the grades? So as I told you earlier, I will give you back your PDF, okay, which is a scan of what you turn in, and also a line by line, point by point, like where you might have lost the point. So if you go like, but I think my answer is right, and you took some points away, you can come back to me, and we'll take a look and make adjustments. All right. So I have to confess that this particular exam was really hard for me to grade, at least initially because I screwed up my script. I did not run the script with a predictable seed number for the random number. And what I usually do is I come up with the questions first, and then I would go back and actually make the program to also output the key, which is what I need to grade. Because without the key, it's really hard to grade when every single exam is different. It's not like I cannot work it out. It's just like, I have to work it out. I have to do the work of, all of you combined in order to do the grading. So I had a few options. I can choose to grade the entire thing manually, which is going to kill me. So I didn't do that. Otherwise, I wouldn't be here today. So what I did was I go like, I wonder if Gemini can actually understand the questions and be able to come up with the answers. Well, let me show you if I still have that here because it's really kind of interesting. Okay, I can just start it up here. So you already have Gemini access, and to get this to work, I had to use the Pro model. The Flash model didn't quite work correctly. And more than that, I also have my own. Where is it now? Uh, this is recent, right there. So I have my CISP 440 exam one grader. I made a gem to do this because I have to give it very specific instructions. Otherwise, it just go all over the place. So what I also did, now I'm showing you this, because I think it is good to one full disclosure, right? Is the professor using AI in his own way? The answer is yeah, definitely. So the script takes the input. Okay, let me go to my folder. Exam CISP 440 1259. That's the semester. So all the exams are also available in markdown format. So it's all kind of it looks like this. I had to convert this in HTML and then from HTML to PDF. So it's kind of like a multi-stage thing to make the exams. So what I did was, I do xclip, self clip, and then do a redirection from a file. Okay, we'll take 000 as an example. So now I have the entire test in the clipboard, and all I have to do is to paste it here and then press enter, and the grader will kind of do its own magic. So we'll, we'll take a look here. It'll give me the key. So, this is how I, ended up with the actual keys to grade the exams. So, in other words, for people who are concerned about the professors using AI to do the grading, that is not true. Okay? The AI was only used to come up with the key, but the evaluation, the comparing between your answer and the key was done by me. So that means, I I take responsibility to any errors that might have happened in the process. Okay, so there we go. So that's how the key is generated. And in the process of doing this, I found that if I use an attachment, if I use the plus key here to upload the markdown file, it does not work the same way. It is really interesting that the AI would actually hallucinate if I use the upload. And it will hallucinate in a very funny way because it will give me the key of an exam that does not exist, but has the same structure as the exams that I have already shown the AI. It's just weird. It is so strange. I cannot even explain how it can possibly happen. But hmm? Yeah, but it was able to parse the paste without a problem. The paste is the exact same content. I don't know what the issue is, because this one is really just me, typing in just pasting the entire file in Markdown, and then the other way is the same file except it's using an upload. So it was really strange, how it would hallucinate with an upload of the file, but if I paste, it does not hallucinate at all. None. Like there was not a single time that it would hallucinate. So strange, but something that if you're using AI, especially Gemini, you'll be careful about uploading files because it doesn't seem to have a very consistent track record of being able to parse the upload. But if you paste, everything seems to be fine. So just really odd. But I do want to demonstrate one thing, which is the AI never got confused about what the questions are asking. So on questions where it is supposed to give me an example, it would give me an example. But for for the answers where it does not need something, it does not give me anything. So I guess I have always been writing in a way, well, that is friendly to the GPT, but not so friendly to people, which is really odd because after all, the GPT is trained on human samples. So very But it also illustrates another point. The AI was able to figure out the answers to everything. The only thing I had to upload was the G function. Okay, so the last question, because it was able to figure out what is Cantor's mapping function, but it's using a different definition where the x and the y are reversed. Okay, because you can kind of imagine that if I traverse the diagonal line this way and another mapping mechanism traverse the diagonal line in the opposite direction, it will still get the job done. So so I had to give it my version of the Cantor's mapping function, but other than that, the GPT was doing everything on its own. It was able to even figure out which of the parts relate to surjection, which part relates to injection, and which part relates to whether a mapping is a function or not. It was able to figure that out. And the other thing that is also extremely interesting, at least to me, because I like to figure out how things work, is you can click on how show thinking, and it would actually tell you everything that goes through the GPT's processing, and kind of show you how it arrived to the answer. So I think that is actually really interesting too. If you're interested in how GPTs work, that kind of gives you an insight into the tool itself. All right. So any questions about this process? No, no questions. All righty. So if there are no questions, what we'll do today is to continue our discussion of not all of no. Oh, we are on this one. Yep. Mm-hmm. No, this is still out of no. All right. So this is the one that we are on. And I realized that I forgot to release the homework assignment last time. So it's like, So if you have been working on it, it's okay. Okay, it's still the same assignment. I just postponed the due date to next Monday. Okay, so if you have been working on it, you have not wasted your time. It's just a matter of, oh, okay, now you have some spare time. All right. So now what we'll be focusing on is proof by contradiction. Okay, and that's section 5.4. It's proof by contradiction. So what we'll do is we're going to go through this entire proof here. Okay, and this may not be the shortest way to do it, but it is a proof nonetheless. So what this proof is doing is trying to show that this implication is always true. Okay, so if the implication is always true, that means we have a theorem, which is basically saying if this is true, then the other side has to be true. So we'll go through this proof by theorem itself, and this is a corollary. Okay, so this is not the theorem itself. This is not proof by contradiction itself. This is a corollary, which is a kind of smaller theorem. It's still a theorem in terms of structure, but it's not called a theorem because it is not as important. Okay, so we're going to go through this step by step, starting on the first line to the second line. What is changed from the first line to the second line? And by the way, this exercise is also useful because I'm illustrating how to use Boolean algebra, which you will need to use in order to convert something into CNF. So from the first line to the second line, what got changed? It is the implication getting changed. So P implies Q is changed to not P or Q. That's the only change. And then from the second line to the third line, it is also just changing this implication to a or, where the left-hand side is negated first. From this line to this line, it is De Morgan's law. So this part here is changed to this part over here, where all the individual component of the or are each one negated, but the operator is changed from a or into an and. That's basically what how De Morgan's law work. And then on the other side, I dissolve the parentheses. So this is called the associative law, which is basically saying if you have an or inside the parentheses and an or outside of the parentheses, then this pair of parentheses can be dissolved because it doesn't do anything. Well, doesn't do anything useful. And then from here to here is De Morgan's law, and okay, that's what I just said. And then from here to here is, oh, this is a OR, and one component of the OR is a bunch of ORs too. So it's basically the same thing. We're dissolving the parentheses. So the removal of the parentheses is kind of nice because it allows us to go like, oh, so that means I can interchange the positioning of things, and it wouldn't change them, the actual meaning, because of the commutative law. So once we remove the extra parentheses, we have more freedom of how we can move the individual components of the or around. And then from here to here is the identity, because anything and true is the original thing. So I apply the same trick over here. And then from here to here, The true is re-expressed as Q or not Q over here. The true is now replaced as also Q or not Q over here. And then from here to here is distribution. So I take this expression here and then distribute it so that we end up with two of those expressions. The same thing over here. This is not R and the or between Q and not Q, and that is also distributed over here. So we basically end up with a much longer expression than we start off with. And then from here to here, I just reorganize things a little bit. You can see that it's just the ordering that got changed. And then from here to here is let's see here. Oh, I combined a few steps, that's on me. It is factoring and then combining with, P or not P is a one. So I basically look at these two and go like, okay, I can do factoring here because they're both ended with not Q, but the component that is different is P or not P, but P or not P is just true. So I end up with a one over here and then the same over here. And then once we have not Q and we also have Q inside a disjunction, those two combine to a true. So once you have a single true in a big OR, the whole thing is going to be true. So that's basically the general idea of this proof. Are we doing okay so far with the individual steps? Okay, so if you cannot follow the individual steps, that's okay because it's a little bit harder when I'm talking and you're just listening. But I would definitely advise you to take a look at this proof and see if you can identify all the steps between each pair of lines. Okay, that would be a worthwhile exercise to do. And then what you can also do is to go to the homework assignment. Okay, go to the CNF homework assignment. The reason why you want to go to the CNF homework assignment is it gives you all the necessary rules that you need to apply for anything in this class. Okay, so we have all of these things. So now you can just kind of write down the number next to the transformation needed or the rule that is applied between each pair of lines, and then that will help you also visualize and having some example of how to apply those, how to apply Boolean algebra in this case. Okay, all right. Or you can do this, right click, and then go to copy to clipboard, copy the entire text command over here, paste it into Gemini and ask Gemini, how the entire proof works. Let's check it out. Okay, I'm curious about whether Gemini can do this or how well we can do it. So let's go ahead and do it. So we'll go ahead and say, explain the following proof. And you have to remember to use dollar sign, to start and stop the LaTeX syntax. So there we go. So we just have a gigantic paste here. Okay, press the enter key. And I'm just curious, does Gemini know how to explain, or at least does it understand the proof? Looks like it does, because otherwise it would just come back and go like, I have no idea what you just talked about. Hmm. All right. So does it break it down? Oh yeah, that is pretty good. So use Gemini to help, okay? Because it actually understands how to do all the proofs. It shows you, what happens between the lines, etc., etc., etc. All right. Are we good so far? Yes. Okay. And you have access to Gemini already. Okay, you just have to go to gemini.google.com after you sign in to your WID at apps.losrios.edu. That's all you need to do. Then you can use the same tools. It's more than a year. I think the contract between the Chancellor's office and Google is 3 year. It's a 3 year contract, but as soon as you're not a student in the community college system, you might lose access to your Google account. So so fail your classes so that you can stay here for another 2 years or so. Hey, life is short, okay? Enjoy. Have a good time. All right. So now we go back to the CNF thing. Okay, so this is not the proof by contradiction or shows that proof by contradiction works. This is just a proof of this implication here. If I already know that P implies Q itself is true, I don't even care what is P and what is Q. It can be a whole expression too. Okay, so P and Q in this case are not variables in the sense of a well-formed formula. In this case, P is just a placeholder for the left-hand side of an implication. Q is a placeholder for the right-hand side of an implication. Each one can be a gigantic, huge expression. Okay, to me, it doesn't matter what it is. So what this is saying is, hey, if you just add a and r on both sides, the implication will still work. It doesn't matter what this and r is. Okay. In other words, whatever p and q are, okay, they're placeholders. The r can have nothing, absolutely nothing to do with p or q, but the end result is the conjunction between p and r implying the conjunction of q and r will still work. Okay, that's what this entire proof is about. Are we good so far? Okay, so now we move on to the actual mechanism of proof by contradiction, which is which is surprisingly simple when we use the corollary. So in the proof of proof by contradiction, so now we just say, now I'll explain this part later, okay, but we'll take a look at the proof by contradiction proof. We'll take a look at the proof of proof by contradiction first. Okay, so let's just say that you have some gigantic expression called psi in this case, and you have some other gigantic expression called phi in this case. If phi implies, if psi implies phi is true, that implies, oh, you can just AND each side of the implication with not phi. Why? Because of the corollary that we talked about earlier. Okay, the corollary basically says you can AND anything you want. Okay, so if this is phi, this can be not phi. So now we do a simplification. Okay, this side we can't really do much about it, so we just have to say, okay, it is just your psi and not phi. But the other side involves an expression and the negation of the very same expression, which means it has to be false. This is proof by contradiction. This is the proof that contradiction works. So now the question is, okay, so what exactly is psi? So we basically just roll back a little bit here. We basically just say, okay, we take everything in iota, we make a gigantic conjunction out of it, okay, and then we just call that our psi. In other words, psi is a conjunction of every element in iota. Are we doing okay so far with that? Are we still remembering what is iota, what it is representing? Everything that is known to be true, everything that is given to be true, or everything that's axiomatically true. Okay, so we take a conjunction of all of those things, we call it psi, I mean phi, psi, sorry, this is psi. And then what exactly is phi? Phi is a theorem of iota. In other words, we start with a bunch of stuff that is known to be true, and then I make a certain statement, and then this is basically we say, okay, if the statement that I'm making, the statement being phi, is implied by everything that is known to be true, then we can say, let's negate, what we actually want to prove, and then make a conjunction with everything that is known to be true. This has to imply false. This implication still has to be true. So tell me, in an implication where the right-hand side is false, but the implication is known to be true, what has to be on the left-hand side? It has to be false. So that means the conjunction of everything that is known to be true and the very same theorem that you want to prove to follow the everything that is given to you, that conjunction is guaranteed to be false. Go like, that that doesn't seem very intuitive, right? So let's go ahead and check out how we can apply proof by contradiction, but not in the context of um, what we are talking about in this class for the time being. So we'll take a look at the pigeonhole principle. Okay, this is the pigeonhole principle, and this is a link to the Wikipedia of the pigeonhole principle. So in mathematics, the pigeonhole principle states that if n items are put into m containers, I'm just double checking to make sure that we are recording, and we are, okay, and n is greater than m, so that means we have more pigeons than there are pigeonholes. Is that okay? All right. So depending on which culture you come from, you might get a little hungry right now. That's what I'm doing right now. I'm going like, oh man, I want to eat some pigeons. So, um, so the idea is if all the pigeons come home, to the pigeonholes, then it is guaranteed that at least one of the pigeonholes has more than one pigeon. So let me say that one more time, okay? So in the classroom setting, you can kind of do it kind of in a slightly different way. We have more students than there are chairs or seats in the classroom. So we are guaranteed if everybody has to sit, okay? I suppose this is not a very friendly situation. So we are guaranteed that at least one chair is going to have two students on it if everybody has to sit on a chair. Does that make sense? Okay. So it makes perfect sense. But how do you prove it? As it turns out, a direct proof is not easy. Even though it makes sense, and we go like, yeah, why do we need to prove this? Well, as it turns out, a formal proof is actually not very is actually quite difficult. So what do? We use proof by contradiction. Okay, so the proof by contradiction goes like this. I can just write it out in a text editor, and this doesn't really need Joplin because I'm not using any format. So we basically say there are n pigeons, okay, n pigeons. We have m pigeonholes, so we can just say m homes or nests, okay. So when the pigeons come back, and n is known to be greater than m, this is given. This is given. Is that okay? So what we want to do is to say at least one nest has more than one pigeons, or we can basically say, one of the pigeonholes has greater than one pigeons. Okay, so how do we prove it? Okay, this is the theorem. Okay, so even at this point, this is important because this is basically saying, what are we putting into the psi that we just talked about? Psi is a conjunction of everything that is known to be true. So in this case, in addition to every rule that we know about in algebra, we also have this random fact of n is greater than m. Okay. The theorem that we want to prove, which in our symbols is called phi, phi is saying, okay, at least one nest has more than one pigeons. So now how do we prove this? Well, we negate phi first. Okay. So now the question is, what is the negation of phi? Negation. What is not phi? So not phi is okay. We'll start with not at least one nest has more than one pigeons. Okay, so how do we translate this? I mean, this doesn't really read correctly. So just to echo my comments earlier, make your English professor proud. What is the best way to describe it is not the case that at least one nest has more than one pigeons? Whew. Can we say that all nests have at the most one pigeon. Would that be okay? Okay, let's write it out here. Okay, so we say all nests have at most one pigeon. Would that be okay? Does everybody understand the this is not phi, okay? So now we make a conjunction, okay? So we make a conjunction of psi, okay? N is greater than m, and because we need to rely on that conjunction, and all nests have at most one pigeon, okay? And how many nests do we have? We have m nests, right? So m nests implies at most m pigeons. So that means, so this means m is greater than or equal to n. Does that make sense? Huh? At Okay, so let me group this so that we know this is basically not phi. Not phi using the symbols that we have defined is going to look like this. Okay, so the first thing we start off with is a negation of phi itself. Phi itself is saying at least one nest has more than one pigeons. So to negate that, we basically have it is not the case that at least one nest has more than one pigeons, but the better way to say in English is all nests have at the most one pigeon. Are we still okay with this? Yes? But using the mathematical symbols that we have talked about here, because we basically say the number of pigeons is n, the number of nests is m. So if all nests have at the most one pigeon, it also means that m nests means at the most m pigeon, because you cannot have there are only m nests, and each one only has at the most one pigeon. So that means at the most we have m pigeons. So that means the number of pigeons, which is n, is less than or equal to m, or m is greater than or equal to n. Does that make sense? So these three over here, they are essentially saying the same thing, except I'm just starting off with the original statement and then put a negation around it. Then we move on to a better representation of exactly the same statement, and then we move on to the mathematical notation of exactly the same statement. Is that okay? So now you put a conjunction, okay? So the conjunction is now saying, okay, all nests have at the most one pigeon is essentially the same thing as m is greater than or equal to n. And now we have a contradiction because this has to be false. So it is not just false, it is has to be false. Because you cannot have m being n greater than m and at the same time m being greater than or equal to n. These two are exclusive. They're mutually exclusive. Is that okay? So that means since we arrive to a contradiction, that is the moment when we go like, oh, okay, we have just proven the pigeonhole principle. So something that cannot be proven directly can be easily proven using the technique called proof by contradiction. You mean this one? Uh-huh. We just have to somehow, look at this conjunction and somehow we have to get to false. Okay? So if you're thinking based on our discussion of the concept of resolution, and we are reducing variables with every single step of resolution until we boil down to false, that is our ticket. Okay, that is our ticket. But before we go back, to talk about that, do we have any questions about the principle of proof by contradiction? Do we understand what psi is representing here and what phi is representing? And how can we establish that psi is the reason of phi? If psi is true, then phi also has to be true. That's what this implication is saying. Now, it is also important that this implication does not say anything about whether psi itself is true or not. Okay? It is simply saying psi being true mean that phi has to be true. If psi is false, then we don't know anything about phi. Is that okay? Are we good so far? Okay. I can show you one more example. Okay, and this one is algebra 2. So we'll go ahead and take a look at another example. So this example is basically saying, okay, all variables are natural numbers, so that I don't have to restate, oh, this is a natural number, this is a natural number, and so on. So I'll just put a gigantic bar here, make sure that we are separating the context. Okay. So now what I want to say is, okay, we'll just look at, variable A, and it is the product of B and C. Okay, this is known. All three are natural numbers. So that means A can be 0, B can be 0, C is also 0, or A is 25, B is 5, and C is also 5, or A is 42, B is 7, and then C is 6. Okay, so in other words, B and C are factors of A. That's all I'm saying. Is that okay? All right. So now we go like, this is our psi. This is what you're told to be true to begin with. Okay, A is the product of B and C. So now we want to look at phi. So this phi is basically saying the square root of A is less than or equal to B, or the square root of A is less than or equal to C. Okay, so why this is important? It is important because when we try to find out whether a number is prime or not, okay, one way is to test it against known prime numbers. Okay, I'll give you an example. Okay, so this is the application. So the application is asking, is 101 a prime number? Okay, that's a question, and you guys can easily look it up and find out whether it is prime or not. But that's besides the point. The point is, how do I test it? Okay, using a really dumb algorithm. So the dumb algorithm is going to say, okay, let's look at 101 mod 2. It is a 1. Okay, 2 is not a factor of 101, so that means I cannot disprove that 101 is a prime number, right? But I still don't know whether it is or not, so we have to move on. So we'll go like, okay, what about mod 3? So if it's mod 3, I believe it is a 2, okay, which is non-zero. The only thing is it has to be non-zero, okay? Okay, that's fine. And let's just say that I'm so lazy with my algorithm, I'll mod 4 also, okay? Now, first of all, is it wrong? Okay, if I check the remainder of 101 mod divided by 4, can I accidentally can I accidentally come to the wrong conclusion that 101 is not prime? Let me say that one more time. Okay, after we test 101 with 2 already, and I just go like, I'm too lazy to keep an array of all the prime numbers, and we'll go ahead and test against 4 also. Is it possible to misclassify 101 as incorrectly as a prime number because of that test? The answer is no. Okay. Does it burn extra processor cycles? Yes. Doesn't have to be done, but it is not wrong in the sense that it won't lead us to the wrong conclusion. Okay, so that means okay, fine, tech. If you want to waste your processing cycle, go ahead. Okay, we mod 5. So mod 5 is 1, okay? And then we go like, I am too lazy to keep track of all the prime numbers, so we're going to mod it with 6. So I think with 6, it is a 5. Okay, there we go. It's just non-prime. Okay, that's all we need. And then we mod it with 7. And I think if you mod it with 7 is, I think 98 is divisible by 7. Yep. So it would be a 3. Okay, there we go. And then we mod it with 8. So 96 again. So that would be still a 5. Mod it with 9. So that would be 99. And so the remainder is going to be 2. And then the next one is 10 with a remainder of 1. And the last one I need to check is 11. So with 11, it is also a remainder of 2. And then right now I go like, I'm done. 101 is a prime number. Can I stop at this point, or do I have to go all the way at least until we prove that, 101 mod 51 has a non-zero remainder? Or can I stop right here? Hmm? All right, so this is why the theorem itself is useful. So what the theorem is trying to say, okay, so we'll go back and take a look at the theorem. So the theorem is basically saying this is important now because if 101 has a factor that is not 1 and itself, being, b and c here, the square root of 101, which is 10 point something, right, has to be less than or equal to one of those two factors. Let me say that one more time, okay? If I substitute a to be the 101, because that's the one that I'm trying to test whether it's a prime or not, okay? What the theorem, what phi is trying to say is the square root of 101 has to be less than or equal to one of the factors, which means once I have tested everything up to the square root of 101, which is 10 point something, so once I reach 11 and I say, okay, I cannot find a factor, up to 11, that means I cannot possibly find a factor other than 101 itself. Does that make sense? Is your algebra up to snuff? No? And you choose computer science as your major? Okay. So something has to change. Okay, I'm not saying you should change your major. Maybe get a little bit stronger of a math background, okay, because you're gonna need it. All right. So this is the reason why the theorem is important. Okay, this example is simply to show you why the theorem itself is useful because it gives me the mathematical basis to stop so that the time complexity of this algorithm is only the square root of the number instead of proportional to the number itself if I want to show or prove that the number is prime. Now that's huge, okay? Because if you think about 1000, okay, or 1001, I only have to prove up to the square root of 1001, which is not too big of a deal, okay? Or 10,001, okay? I only have to go up to 101 and I'm all done, okay? Because if there is a factor other than the number itself, because factors come in pairs. Does that make sense? Give you an example. 42, okay? 42 has a lot of factors. I'm not looking at just the prime factors. So let's look at 6 and 7. That's a pair. It is also 2 and 21. That's a pair, right? If you look at 9, which is actually a square itself, it is 3 versus 3. So I'm basically saying if you look at the pair of the factors of a number, one of the items of the pair has to be less than or equal to the square root of the number. That's basically what I'm saying. Is that okay? So does that make sense? Okay, let's look at 42. Okay, if you look at 42, and we're looking at the pair of factors that is as close as possible, which is 6 and 7, right? 6 squared is 36, so not quite meeting the criteria, okay? Because but 7 times 7 is 49. So one of them is less than the square root of the number. I take it back. The 6 is the one that is less than the square root, less than or equal to the square root of the number itself. What about 36? Okay, 36 is 6 times 6, right? So I look at that pair of 6, 6. Is at least one of those two less than or equal to the square root of 36? The key is at least one. In this case, both of them are less than or equal to the square root of the number because 36 itself is the square of 6. Are we still doing okay so far? Okay, so this is just the application of the theorem, not the proof of the theorem. So now we look at this, okay, and we go like, okay, I have to negate it first. So not phi is the negation of what we are saying here. So this is basically saying, okay, it is not the case that the square root of a is less than or equal to b, or the square root of a is less than or equal to less than or equal to c. Okay, and I don't like to look at square roots, so I'm going to change it a little bit and say a times a is less than, oops, a times a, no, a is less than or equal to b squared, okay, or b times b, or a is less than or equal to c times c. Okay, is that okay? I'm checking your algebra again, okay, because we know a, b, and c are all non-negative numbers, right? So that means if the square root of a is less than or equal to b, and I square both sides of the less than or equal to, well, the inequality should still hold. That's basically what I'm saying. Are we good? All right. Okay, now we look at this and go like, but it is kind of cumbersome to say it is not the case that a is less than b squared or a is less than c squared, less than or equal to c squared. So we're gonna do some, kind of manipulation so the whole thing is easy to read. The first one is De Morgan's law, because we have a negation applied on top of a or, so that means De Morgan's law is applicable. Now, just because it's applicable doesn't mean that it is nice to use, but in this case, it really is quite nice. Okay, so we look at this whole thing, and then we use and here because we have to have a conjunction with the negation of the other side, which is a is less than or equal to c times c, like so. But instead of saying it is not the case that something is less than or equal to something else, why not just say a is greater than that, right? So now we just go like, okay, that's the same as saying a is greater than b times b, and a is greater than or equal to c times c. Are we doing okay so far in terms of the derivation of the negation of phi, starting with really just the negation of phi itself, but then we use algebra to derive the whole thing into a is greater than b squared and a is greater than or equal to c squared. Are we good? All right. So now we use some more algebra, okay? And then we say that, oh, okay, this implies, okay, what does it imply? It implies a times a is greater than b times b times c times c. Does that make sense from the perspective of algebra? A is non-negative, okay? B times b is definitely non-negative because it's a square. C times c is also guaranteed to be non-negative, right? So if we, I think I made a mistake here. This is supposed to be greater than, not greater than or equal to. So just minor mistake, fix. Okay, so now can I just say, okay, since A is greater than this and A is greater than that, then I can just combine the two A's, multiply those two, combine the other side of the inequality and make a product out of those two. This inequality should still hold because everything is non-negative. Is that okay? Okay. So now you look at this and go like, okay, let's use some more algebra. So if you're getting a headache because I'm using algebra, I'm sorry, but I'm actually not. Okay. Is that okay? I'm just using the commutative law and also the associative law of multiplication. Associative first to get rid of all the extra parentheses that are not needed. And then we use commutative to move things around because I have two B's over here. I still have two B's over here. I had two C's over here. I still have two C's over here. The whole thing is just one gigantic multiplication. So that should not be a problem because what is B times C? What is known about B times C? It is A. Oh, okay, okay, wait. This is the whole cool thing, okay? So this whole thing says, A times A is now greater than A times A, which has to be false. Is that okay? Are we doing okay? So now we have a contradiction. So when you combine So this by itself is already a contradiction, but it is because of the negation of not phi. So that means if you combine psi and not phi in this case, and then we put extra parentheses to emphasize that we are negating just the phi itself, this is now guaranteed to be false. So because the conjunction of psi and not phi is false, according to the structure of proof by contradiction, we now know that phi is implied by psi. That's all we can say, okay? This is all we are trying to say is psi, which is this, implies phi, which is this. So that means if you tell me that A is the product of B and C, like make A 48, okay? Make B 8, make C 6, okay? So that makes this equality true. Then I can tell you that one of the square root, excuse me, one of the, I think I just messed up. I think I just messed up here because I think this is supposed to be greater than or equal to. This is supposed to be greater than or equal to. Uh, Let me think. Thinking. If there's a root, if there's a factor, then one of them has to be less than or equal to the square root. So they're supposed to be like that. Okay, let me see if that makes sense or not. Put all of these as it still boiled down to the same thing. It's just which side is the A times A. So okay, it is still going to work, but it's going to work the opposite way. And you can see it still works, but this is the correct proof. Okay, I do apologize that I made the phi incorrect in the first place. So the phi is supposed to be at least one of the factor of a is less than or equal to the square root of a. But we still arrive to the same conclusion of, oh, okay, we still get to the same conclusion that a times a is less than a times a, which is false. Is that okay? All right. So this is proof by contradiction, in action. Are we doing okay? Let's just say that you're not following along, okay? And you go like, okay, when I go home, I'm gonna use, Gemini to help me with this proof here. How do you formulate your prompt to Gemini? So I'm training you to use AI because I think it is a really great tool. So you create a new chat, okay? You just say, okay, um, you just have to name all the conditions, right? So you have to say, A, B, and C are all natural numbers, okay? Um, use proof by contradiction that, okay? You just have to say, A equals to B times C implies, and then we can use your square root, okay? So we imply that one of them has to be less than or equal to the square root. So we can say B is less than or equal to the square root of A, or C is less than the square root of A. Okay, I think that is all we need to do here. Okay, this is what we need to prove. And just go ahead and press the enter key, and I think Gemini can do this. I wanted to show you the steps. Yep. So that you can actually look at the steps, as explained by Gemini. Yeah. What? What? Okay, wait, wait, wait. I'm not making connections there. It has to guarantee false. Um, okay, so let's go back to the mouse pad here. So this is known, this is told, you are told about this, okay? So the idea is if this is true, if psi is true, then we also want we want to conclude that this also has to be true. The way to, yeah, yeah. So so what we see in Gemini is really the same thing. It basically arrived to the same conclusion that the contradiction leads to, well, I should let me take it back. The negation of the theorem leads to A is greater than A. No, no, this is a guaranteed contradiction. This is a guaranteed contradiction. Okay, let me go back to here. So that means, if you negate phi and you combine it with psi, then it is a guaranteed contradiction. So the way we utilize psi in this entire process is when we see B times C, we can replace it with A. That is how psi is utilized in this implication here. Okay, I'm proving what? Okay, let's not use pronouns. Point out, okay, are you talking about psi? Are you talking about phi? Yes. By proving the negation of phi combined with psi would lead to a contradiction, we have just proven that phi is a result of psi. That'll be good? You have to arrive to a contradiction that is guaranteed. Yep, yep. But because of the way we define A, B, and C over here, so it is usually using either A squared being less than A squared or A is less than A. So the hmm? Well, proofs are pretty hard to test in an exam. So, I'm inclining not to do that. Um, but in this case, you can also see how Gemini is able to basically follow pretty much the same steps to come to the same conclusion. Okay, and you can ask it specific questions too. You can say, okay, I'm not really understanding step two. Can you elaborate or expand on the step two? And that's the one thing that's nice about Gemini is you wake up 2 a.m. in the morning, and then this is just nagging you in the head. It's like, oh, I'm not quite understanding that step. Just get to your computer, go back to the conversation, right? You can have like 20 conversations going on with your Gemini. Go back to this one and say, I'm not really sure of how step two works. Can you elaborate on step two? I can tell you, when I was working on my dissertation, some of the most difficult parts of the proof happened when I was dreaming. So I would wake up 2 a.m. in the morning, scramble to find paper and pen so I can jot down the actual step of the proof. This happened to me multiple times. I solved problems in my dream. Huh? Oh, I cannot do that. I have to watch some really. The way I go to sleep, in peace, is to watch some kind of either action movies or scary movies or horror movies. That is how I fall asleep. It's like, oh, this is so ridiculous. Oh, this is not possible. Mm-mm, hmm. Oh, I'm not gonna sleep after watching that. I'll be going to Amazon after that, which means I'm not gonna sleep for the next 2 days because I'll be looking for the best deal, reading all the comments and rating and whatnot. Yeah, that is definitely not gonna go to, not leading to sleep at all. Okay. All right. So are we understanding the basic idea of proof by contradiction? You're given certain things and go like, okay, this is what you're given with. Okay. If what you're given with is true, then we want to show that thing is also true too. Okay. So that's the whole idea of proof by that's the idea of proving. But proof by contradiction is saying, let's negate what you want to prove in the first place, negate it, and then use the and to connect it to everything that is known to be true. And if that leads to a contradiction, which is just false, okay, then we are good. Then we have just proven the very same thing that you want to prove to be the consequence of everything that is given to you to be true. Then that completes the process. So let's go ahead and actually watch this in action. Okay. So what we'll do is we're going to go back to the module because it does have examples. So now we use the example, and then for no particular reason, we say that this particular side is always true. Okay, or this is what is on the left-hand side of the implication, and this is what is on the right-hand side of the implication. We want to see if that implication is always true. Are we good so far? Okay, so I'm going to keep showing you this part here when I'm using the mouse pad to actually work on this on the side. Now, obviously, I cannot use Greek letters in a plain text editor, so I'm just going to have to spell out psi. So psi is the negation. Well, we have already shown that this particular psi can be converted to a CNF like this. Okay, so we go like, okay, this is the same thing as not P or R. Oops, not P or R, and okay, not P or Q. Okay, so this is from the previous class. Okay, in the previous class, we looked at the expression and then we converted the whole expression to a CNF, which is what we see in over here. So now we have phi, okay? So phi is not t implies p. So now we have to look at what is not phi. So not phi is going to be the negation of that, okay? So we'll go ahead and take care of this, which is then the negation of not t or p because of the definition of implication. And then we simplify things as we go along so that things are actually easier to read. So now we have just t or p, but we have to negate it. And so that's why we have to apply De Morgan's law, okay, which is just not t and not p. And that is CNF. Not t and not p is a CNF because it is a conjunction of deformed disjunctions. This is a deformed disjunction because we can always add an or false to every single one to turn it into a proper disjunction. Are we good so far? Okay. Oh, sure. Better? Okay. All right. So now the question is, what about that whole thing, which is the conjunction of what is given to you, which is not P or R, not P or Q, and then we make a conjunction with not phi. So not phi is not T or false, and then we also have not P or false. So now the question is, does this imply false? Okay, we don't know. Okay, we want to see if it does imply false or not. So what do? We use resolution. Okay. So in this case, can we perform a single step of resolution? How do we apply resolution? What are we looking for? We are not we're not looking for contradiction. We are really just trying to apply resolution. How do we apply resolution? Okay. Do we know where to find the discussion of resolution? Go with a definition. Okay. Don't guess what it is. Find it so that we know for sure what it looks like. Okay, so let me put this on top so I can scroll in the background without affecting the front. So resolution is something that we talked about like way earlier than this. Okay, so keep scrolling right there, almost. There we go. This is resolution. This is the pattern that we're looking for. Okay, in other words, can I find two of these disjunctions where one has a variable mentioned that is not negated and the other one has the same variable but negated? And the answer is nope, we cannot find anything like that. Okay, look at this one here. Okay, if we focus on this one, then we're asking, does anyone else have P that is not negated in the disjunction? Nope, 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 right? We can also ask, what about not R? Because we have R here. So if anyone has the negation of R, we can perform resolution. Nope, nope, nope. Okay. So we are now done with the first expression. It cannot resolve with anything else. Then we ask the same question for the second disjunction. Okay, we already know that nobody has P, so we can ignore that. But now we can ask, who has a negation of Q? Nope and nope. Okay, so that means there's nothing that we can resolve here. Then we look at the third one, which is just a single not t, which can only resolve with anything that has t not negated in it, right? So we go like, no, that is not working. And now we look at the last one, okay, which is not P. But since it's the very last one left, there's nothing that can resolve with it because we don't have any additional disjunctions that can potentially to resolve with this one. So now we say this one does not resolve to false. So what is the conclusion? The conclusion is simply phi is not a theorem of psi. Okay, which is not to say that phi is false. Okay, we don't know whether phi is false or not. We just know that it is not a theorem of psi, which means it is not implied by psi. That's the only conclusion. Are we good so far? Yes. by concluding that we cannot resolve to false. In fact, we cannot perform a single step of resolution in this case. Hmm? Well, you tell me. I know. I'm forcing you to think about it. Okay, how do we think about this? Okay, what happens if tech dies and you cannot ask me, even if I wanted to answer your question? You go like, but then surely they will have somebody else to teach the class if something is to happen to tech. Okay, let's not think about it that way. Let's just think that what if tech cannot answer the question or will not, like in this case, answer the question? What do we do? The question is whether the highlighted portion is a CNF or not. Okay, so the first question is what is it actually saying? Okay, what is this notation? It is saying not P or R and not P or Q and blah blah blah. So do we understand that part? I mean, without that part, there's nothing. We cannot move forward. In other words, do we understand the notation of the highlighted portion by itself? So we see some nods. Are we good? Since you asked the question in the first place, are we good? No. Okay. So that becomes a notation issue, right? So I'm not trying to be mean, okay? What I'm trying to do is to find out where the disconnect is, okay? So the disconnection in this case at least starts with not understanding the notation. So now we have to go back to the notations, right? So we have to go all the way back to the beginning of this class, starting with, not this one, oh, maybe this one. Go to Boolean operators, because that is the module that talks about the notations of how we represent conjunction, disjunction, and negation. So when we go to conjunction, this is what conjunction can be represented. X and Y is represented like this in C++. In mathematical symbol, it looks like this, but sometimes it is simplified to this using a multiplication dot in between, or even this. So that is what connects and go like, oh, okay. So that means when we see something like this lack of symbol in between is a multiplication, and the multiplication means conjunction. Okay. So now we look at what about the plus? Okay, how do we use plus in a Boolean expression? So disjunction can also be represented using a plus. So that's a symbol, right? And then what about negation? What about the exclamation point? The exclamation point is the actual C++ operator representing negation. So that means, oh, okay, so this whole thing is a gigantic conjunction that has four parts. The first part of the conjunction is not P or R. The second part is not P or Q. The third part is not T or zero, false. Not P or false is the last component. Okay, so are we good so far? Okay, just in terms of the notation. So once we get the notation out of the way, then we ask, okay, is that a CNF? So now we have to go back to the more recent note, or the one that we are looking at, which is this one here. And then we go to the section that talks about the CNF, okay? Not the completeness, but really just, how do we define the CNF? So right here, okay? So now we're asking, um, hmm? Yeah, this is under resolution. So now we have to ask in a CNF. Okay, so it is described here. Okay, so in this case, we are saying, okay, what is a well-formed formula? A well-formed formula is going to be an OR of stuff. Okay, what is each stuff what is the qualification of each thing in the OR? It has to be a disjunctive element. What is a disjunctive element? A disjunctive element would be something that is coming straight from alpha, or something that is the negation of an element of alpha. So now you look at each one of this, and then you ask, uh, is this coming from alpha? Yes. Is this coming from alpha or the negation thereof? Yes. So that means this disjunction here is a well-formed formula. This is also a well-formed formula. This is also a well-formed formula. So each one of the components is a well-formed formula. C and F is basically saying it is a conjunction of all the well-formed formulae, okay, or as long as every component of the conjunction is a well-formed formula, then the conjunction itself is a CNF. So that is kind of how we make all the connections. Are we doing okay so far? Okay. And the other thing we can also do is to look at the CNFs that are already formulated. So we look at examples of a CNF. This is a CNF, okay? So do we see a pattern here? Well, you look at each expression, you go like, okay, it is a conjunction of things. Is this a conjunction of things? Yes. Of each thing, it is a disjunction of some other thing. Is in this case, is each sub-expression a disjunction of something? Yes. What about those things inside the disjunction? It looks like we can have the PKRST by itself or the negation of one of the PKRSTs. You look at this thing here and go like, okay, is that true? Okay, so now, so using the example, you can also get a second way of looking at what is a CNF. Are we okay so far? All right. So because this one does not resolve to anything, we go like, okay, so show me something that actually resolved to false. And we only got about 2 minutes left, but I think we can do it because we have phi 1. Okay, so phi 1 or phi prime is here. So this is phi prime. So we'll go ahead and see what we can do with phi prime. So phi prime is P implies the negation of Q. Okay, so not phi prime is going to be just the negation of P implies not Q. So now we have to see what we can do here to convert the whole thing into a CNF. The first step, for me at least, is always converting the implication to an OR. So now we have not P or not Q. And then since this is the negation of an OR, we mandatorily have to apply De Morgan's law whenever De Morgan's law is applicable. So that means, oh, okay, so that means this is just P and Q, okay, after De Morgan's law, and P and Q by itself is already CNF because P by itself is a disjunction in disguise, Q by itself is also a disjunction in disguise. So now we do a concatenation with the other two things, which is coming from psi, okay, and then we put these two here. So now we ask, can we apply resolution? In other words, I look at one of these and then I ask, does anyone else have a P? Oh yeah, I have a P over here. So now we can apply resolution. So after that resolution, we end up with a single expression that is a R. Okay, and then we continue to ask the question, okay, does anyone have not R? Nobody has not R, so nobody responds to it. Okay, that means we are done with the first component of the CNF. We look at the second component of the CNF, and then we ask very much the same question. Okay, I think I made a mistake somewhere. Mm, maybe not. Hmm. Something is not making sense here. Okay. No, that is fine. I think it is. We got R over here. We will get Q. Okay, so another resolution. We got Q. Okay, so I think I made a mistake somewhere along the line. All right, we'll You guys can try to spot my mistake because the solution is already here, right? So you can actually look at the solution. Um, and then we'll talk about this on Wednesday. I mean, you can kind of, so in the solution, we can see how this not P and P is, okay, I see where the mistake is. The Q is supposed to be negated in the original thing. This Q is supposed to be negated. There we go. Okay, so that would make sense because we can do the resolution between this one and the P, and um, we would end up with not Q. And then when we look at the Q and the not Q, because these are implicitly just having a or false here, right? There's an or false here. So when we look at these two, then they would resolve to a false. But because the false is inside a gigantic conjunction, the whole conjunction is false. So we do, so there's an implication of um, phi prime and psi and not phi prime will lead to a contradiction. So, and then by proof by contradiction, we now know that phi prime is a theorem of psi. So we're going to rerun this last part on Wednesday just to make sure that we understand how this works. So I made a mistake. Yes, my mistake is, this not Q, the Q is supposed to be negated in not P or Q. So I made an incorrect copy earlier. So this is supposed to be negated too. Alrighty, let me stop the recorder.